Hello everyone. So today we are going to review the main ideas behind the Octect rule and bonding in organic molecules. Okay, so first thing we need to know is what are the most common atoms found in organic molecules? And that is carbon, obviously hydrogen, nitrogen, and oxygen. Okay, so if we are going to think about bonding in organic molecules, we have to first take a look at the electronic distribution of one of each of these atoms. We are going to ignore obviously hydrogen since hydrogen only has one electron. And let's quickly look at the electronic distribution of carbon, nitrogen, and oxygen. So carbon atomic number, as everybody should know, is 6. So if the atomic number of carbon is 6, it means that it has 6 protons, and therefore a neutral carbon atom will have 6 electrons. So as uh, we know, here is the electronic diagram, the energy diagram for the orbital. So we fill up from bottom to top, adding 2 electrons at a time. So in level 1s, we're going to add 2 electrons here. In level 2s, that's another 2, so that's a total of 4. And then the total number is 6, so we need to add 2 more. So we will add 1 more. Let's pick it up. Sorry. So we're going to add 1 more in 2 more in the 2p orbitals, and because these orbitals have the same energy, we add 1 here, and then we add a second one here. Okay, so remember, when we have degenerate orbitals, meaning orbitals with the same energy level, you start filling them up by placing 1 electron in each of them. Once they are full, you go to the next. So carbon has 6 electrons. This is the electronic distribution of carbon. Nitrogen has 7 electrons. So the electronic distribution will be that of carbon plus 1 electron. So let's add that up. So I'm gonna color code this nitrogen for you guys to follow with a blue color. And then the extra electron for nitrogen is gonna also be blue. Remember, the extra electron must be added in the empty p orbital. So that could be the electronic distribution for nitrogen. And then finally for oxygen, which atomic number is 8, we will only have to add 1 extra electron after nitrogen. So I'm going to color code this with the red, and that electron will be added obviously in the first orbital. So let's do this quickly, and I'm going to color code these electrons as red. So that could be the electronic distribution of oxygen. So guys, look at the electronic distribution of carbon, nitrogen, and oxygen. What do they have in common? So what they have in common is the valence shell. So the 3 atoms have the same valence shell, which is shell number 2. Remember, in shell number 2, the maximum number of electrons allowed is 8, and there are 4 orbitals, 1s, and 3p orbitals in that valence shell. The total number of orbitals in the valence shell for carbon, nitrogen, and oxygen is the same, 4 orbitals. They differ in the number of valence electrons, which is 4, 5, and 6. Remember, valence electrons is the same as the group number, and valence shell is the same as the row number in the periodic table. So what information can we extract out of this? Because the valence shell for these 3 atoms is shell number 2, and in that valence shell there are only 4 orbitals. The maximum number of bonds for these atoms will be obviously 4 bonds. So guys, in organic chemistry, which is the chemistry of carbon, and this is something that I always emphasize in my classes, the maximum number of bonds for a carbon atom is 4. Why is that? Because once again, there are only 4 orbitals in the valence shell of carbon. Therefore, there is no room for more bonding than 4 bonds. Okay? Well, now, with that in mind, I'm thinking about the valence shell, knowing the valence electrons and the number of bonds, we can think what is the bonding, or what type of bonding do we find in organic molecules. And in organic molecules, what we find always, always, always will be covalent bonds. And here is where the octet rule uh, plays a big, big role in understanding the bonding in organic molecules. So what is the octet rule? So the octet rule says that every element tends to react in such way that they complete a full valence shell. Why is that? Because that's stability. That's how they achieve stability, and this was concluded out of the electronic distribution of the noble gases, right? All the noble gases are in group 8. They have a full valence shell. They are highly stable. So what the octet rule is telling you that if you apply this to organic molecules, in this case to the elements in the second row of the periodic table, they will tend to react in such way as to complete 8 electrons in the valence shell. Okay? Once again, because valence shell is shell number 2, and in shell number 2 there are only 4 orbitals. So that would be the driving force for bonding in organic molecules, and the bonds that organic molecules are forming are called covalent bonds. So what exactly do I mean by covalent bonds? So I'm going to give you an example of what is a covalent bond. So a covalent bond is formed when 2 atoms share electrons to form a new bond. Let's say, for example, we have a chlorine atom. Chlorine is in group 7, therefore it has 7 electrons in the valence shell. So let's complete the Lewis structure of chlorine, 6, and I'm going to add a 7th electron here. Okay, so if I react 2 chlorine atoms, what's going to happen is each chlorine atom has 7 electrons in the valence shell. So the way for the chlorine atom to react would be to complete, once again, 8 electrons in the valence shell. To complete 8, it will need to add 1. So both atoms are in the same scenario. They need to add 1 electron to complete 8. So what's going to happen here is they are both going to share that extra electron. And by sharing that extra electron, they're going to form a new bond, which is called a covalent bond. So sharing these electrons, forming a new bond, and look at how I'm using the curved arrows to indicate that both atoms are going to share an electron, and we show this by means of a line, right? So a line means a bond. A bond has 2 electrons, 2 orbitals are participating in a bond, and that would be a chlorine molecule, okay? And this is a covalent bond. It is a covalent bond because, once again, the electrons are shared between the 2 atoms forming the bond. So covalent bonds, I'm going to write over here, sharing electrons. Okay, so in the case of the chlorine molecule, so this is homonuclear diatomic molecule, both atoms having the same electronegativity, so they share the electrons equally. So electrons are equally shared. Therefore, we call this a nonpolar covalent bond. So when the 2 atoms have a similar electronegativity, below 0.5, they will share these electrons pretty much equally, and that is classified as a nonpolar covalent bond. What is a nonpolar covalent bond? It's a bond in which both atoms are pulling the electron with the same strength. Therefore, the 2 electrons are pretty much in the middle of the axis in between the 2 nuclei of the atoms. A second scenario could be when you have, for example, the bond in between hydrogen atom, hydrogen has one electron, as everybody should know. So for a hydrogen to complete a full valence shell, we'll need to add another electron since it's 1s, and in 1s there are two orbitals. And let's say that hydrogen atom is reacting with a chlorine atom. So chlorine has 7 electrons in the valence shell. So for a hydrogen to react with a chlorine, it means that obviously if both of them share one electron from each, hydrogen will have 2 electrons in the valence shell. Chlorine will have 8 electrons in the valence shell, meaning that obviously this would be both atoms achieving stability with 8 electrons chlorine and 2 electrons in the valence shell for hydrogen. So they both will have a full valence shell, okay? So how do we show that? We show that by, once again, a line. A line is the covalent bond. On one side we have one atom, which is the chlorine atom. In the other side we have a hydrogen atom, which is the second atom forming the bond. If we are going to complete the Lewis structure, then we just add 6 dots here on the chlorine. And now we have, once again, a molecule of hydrochloric acid in which the bonding between the hydrogen and the chlorine is a covalent bond. Now in this case, chlorine is more electronegative than hydrogen. Therefore, these electrons in the covalent bond are not equally shared, meaning that the most electronegative atoms is pulling the electrons toward itself, right? So that is what we call in organic chemistry a polar covalent bond. So when you have two atoms with significant difference in electronegativity, I'm gonna say electronegativity difference in between 0.5 and 1.9. 1.9. So when we have that situation, we can say that this is a polar covalent bond. What do I mean by a polar covalent bond? A polar covalent bond is a covalent bond in which, once again, one of the atoms is more polar than the second one, therefore it's pulling the electrons toward itself harder. Guys, this electron pulling will basically creates what we call in organic chemistry a dipole, meaning that in one of the atoms there will be a fraction of negative charge, and in the second atom there will be a fraction of positive charge. This is because, once again, the difference in electronegativity makes the electron density around the chlorine atom to be slightly higher and the electron density around the hydrogen atom to be slightly lower. Okay, so this is a polar covalent bond. So when we look at organic molecules, and I gave you one example here, let's say in an organic molecule like this, a simple organic molecule, we have three different bonds here, four types of different bonds. We have carbon-hydrogen bonds, we have carbon-carbon bonds, we have a carbon-oxygen bond, and we have a carbon-halogen bond, okay? So the carbon-carbon bonds, I'm gonna list this over here. The carbon-carbon bonds, obviously, carbons is two atoms that are the same. They have the same electronegativity. They share the electrons. So this is a nonpolar covalent bond. The carbon-hydrogen bonds, if you look at the electronegativity of carbon and that of the hydrogen, you'll see the difference in electronegativity is very tiny, around 0.4. Therefore, they have very similar electronegativity. Carbon and hydrogen, they form nonpolar covalent bonds. Now, the carbon-halogen bonds is a different thing. Halogens are more electronegative than carbon, meaning that they are pulling the electrons of the covalent bond more toward themselves. So the electrons in between carbon and hydrogens are not equally shared. So this is a polar covalent bond. And we're gonna say that it's polarized toward the halogen atom. That actually means when I said it's polarized toward the halogen atom, it means that the electrons are closer to the halogen, meaning that once again, because of the difference in electronegativity, there will be a fraction of negative charge over the halogen, and there will be a fraction of positive charge over the carbon atom. This is extremely important, guys, because this will allow you to understand later on reactivity in organic chemistry. And then finally, the carbon-oxygen bond. Once again, oxygen and carbon are on the same row of the periodic table. Oxygen being way more electronegative than carbon, right? Same valence shell, and then larger number of protons in oxygen. So there is a stronger attraction for the electrons in the outer shell. That's why oxygen is more electronegative. So this is, once again, difference in electronegativity between oxygen and carbon is substantial. So this is a polar covalent bond. And therefore, because oxygen is more electronegative than carbon, this bond will be polarized toward oxygen. So we're gonna show that here. And by that I mean that once again, there is a fraction of negative charge over the oxygen atom, and there will be a fraction of positive charge over the carbon atom, okay? So that's how you can classify covalent bonds in organic molecules. So once again, octet rule, atoms in the second row react as to complete 8 electrons in the valence shell. That's how they achieve stability. Okay? Now, bonding is by sharing electrons. Those are covalent bonds. You can share the electrons equally when both atoms have the same or similar electronegativity. That's a nonpolar covalent bond. I gave you the example here of carbon-carbon bonds or carbon-hydrogen bonds. Or the electrons can be shared unequally when one of the atoms is more electronegative than the other. In that case, the bond is polarized always toward the highest electronegative atom, in this case oxygen, in this case the halogen, and that will increase the electron density around these atoms, leading to a fraction of negative charge over the most electronegative atom and a fraction of positive charge or electron deficiency in the less electronegative atom, in this case the carbon atom. Okay, so lastly, I want to just say that covalent bonds can also be classified into sigma and pi. This is very important. Remember, guys, a sigma bond, I talk about this in some other videos, is when there is a direct overlapping of atomic or hybrid orbitals. So by direct overlapping means that physically both orbitals participating in the bonds are overlapping. So the electron density is right around the nucleus of the atom. So if you draw a line in between both atoms, an axis between the nuclei of both atoms, you will see, and sorry about this, if you draw an axis around the nuclei of both atoms, you will see that the electron density is right in between them. That's a sigma bond, okay? Sigma bond, I'm gonna type it over here just in case. Direct overlapping of atomic or hybrid orbitals. If you don't know what is the hybrid orbitals, I'll show you a video later on to understand hybridization. And a pi bond is a different thing, it's a different monster, guys. A pi bond, remember, is side-by-side overlapping of pure orbitals, okay? So a big difference in between sigma and pi, okay? This is a pi bond, side-by-side overlapping of pure orbitals. Sigma, direct overlapping of atomic or hybrid orbitals. So I'm gonna say over here, right over here, side-by-side overlapping of pure orbitals. All right. And yeah, that's how we classify bonding in organic molecules. We can talk more about sigma and pi bonds. I will mention that in a different video, but overall I wanted to just give you a brief overview of how you can envision bonding in between atoms in organic molecules. I hope this is useful. If you have questions, feel free to ask.